Okay, here we go. Notes on 10.1. This is the basics about circles. I know we've talked a little bit about circles already, but we're going to go a little bit more into the details, including some theorems. Yay, proofs are back. All right. First of all, what is a circle? Kind of a weird definition. It is a collection of points that are equidistant from a particular point. All right? So if you find a point, and then you go out, say a distance, call that x, or let's call it r for radius. And then I go out that same distance, r, and then I go out that same distance, r. I will eventually find a collection of points that form a circle. Okay? So, that is how we define a circle. What is the center? Well, that point that is equidistant from all the points on the circle. What is the radius? The radius is the distance between the center and any point. And then, obviously, congruent circles would have would have equal radiuses, the same distance from the center to that point. Here is a fancy term, which you might not have heard, concentric circles. These are circles that share the same center. Okay? I'm not too sure what the co-word is here. But if you take a circle, and then you draw another center with that same circle with the same center, then those are called concentric circles. Anyways, continuing. Oh, I know, coplanar. Phew. So they have to lie on the same plane. All right, continuing on. So interior, exterior circle. And then obviously the circle itself is that space or that line, which is the collection of those points, right, around the center. So you can think of that as like three different regions: on the circle, in the circle, out of the circle. All right, what is first of all, chord? A chord is any segment that joins 2 points on the circle. So go ahead and draw a circle like that and draw a point, 2 points on the circle anywhere, and just connect them. That's a chord. We have special chords called diameters. They not only also go from point to point on the circle, but they go through what we call the center, right? So a diameter is a special chord. Why? Contains the center. And then a radius goes from the center, obviously, to the edge. So that is not a chord. Circumference, the distance around. Keep in mind, this is a one-dimensional shape, whereas the area is a two-dimensional shape. And obviously that is the area of the interior of the circle. And then here are the kind of the theorems of the section, which you will be quoting in the proofs. If the radius bisects a chord, then it is perpendicular to the chord. And then we have the converse of that, and that is that if the radius is perpendicular to the chord, then it also bisects the chord. So, if I give you this, then you automatically know those two segments are the same. And if we know that the segments are the same, then we know that they are perpendicular. So this can be summarized with this little chord radius relationship, and that is that in general, with chord and radiuses, if they're perpendicular to each other, then they bisect. And if they bisect, then they're perpendicular. So it's a neat little, what we call a biconditional, because it goes both ways. Finally, a kind of takeoff of that, and that is that if I have a segment which is both perpendicular and a bisector, then guess what? That goes through the center. So a perpendicular bisector of the chord goes through the center. In fact, you end up creating what would be known as a radius or a diameter. Okay? All right. So here is possibly a proof and then a problem, and then off you go to your work. All right. So we are given some information in this problem. We have a perpendicular relationship, which is, again, that proof that we just finished talking about. So PR is perpendicular to ST. We want to show that these two segments on the outside are congruent. Well, hopefully this isn't too strange for you, but guess what? Do you see two triangles? If you see triangles, try to make them congruent. Kind of back to that game. So let's see. I have a perpendicular, so I think we could say, I'm going to call it angle 1 and angle 2. So angle 1 and angle 2 are right. Okay, that's the definition of right angles. And then angle 1 is congruent to angle 2 by the right angle theorem. Wow, ever since chapter 1. Line 4. We now pick up for free that those legs are congruent. Okay, so we would know that angle RS is congruent to RT. And there we know that if a radius is a bisector, we don't know that it's a bisector, we know that it's perpendicular, right? If the radius is perpendicular, then it's a bisector. All right. I'm going to say PR is congruent to PR by the reflexive property. Hope you like my rock and roll in the background. So I think we have, by the side angle side theorem, that these two triangles are congruent. Triangle PRS is congruent to triangle PRT. And then, yeah, CPCTC, we can pick up that PS is congruent to PT. Hurrah! All right. And then finally, a problem where you have to kind of solve puzzles. They'll give you pieces of a chord. So here we are given a circle with radius 13 millimeters, a length of chord of 10. So we kind of know this. Well, immediately we know that then the radius is 6.5. Okay, half of 13. And then let's make a right triangle by drawing a line which is perpendicular. So now I have a right triangle, And I know that one leg is 5. The hypotenuse is 6.5. And then I want to find the distance from the chord to the center. And that is that distance right there. I forgot to go through that. That was a little note back up here, which I kind of ran right over. The distance from the center of a circle to a chord is the measure of the perpendicular segment from the center to the chord. Suffice to say that if I want to measure the distance of this chord, PQ, to the center, I'm not going to measure this, I'm not going to measure this, or this, or this. I'm going to measure this line here, which is the perpendicular. Okay? So that's why we were going for this particular distance, and that's why we create that particular triangle. All right, so then you're going to use your Pythagorean 6.5 squared minus 5 squared. And I'm not too sure what this is, but I'm sure your calculators will approximate it. Oh, is this I wonder if this is a family. No, it's not. 13, 10. No, that's not a family. Okay. Well, we would just approximate this out and then take the square root of that to find x. Okay? All right, good luck in your homework.